Today we are going to show you how to use Elfen gd3D for glass design. There are 3 stages: review design thickness, test tooling geometry and machine setting. Finally, review and iterate the tooling geometry or machine settings. Stage 1. Review design thickness. In this step, different loading conditions are applied on the design thickness and the stresses are compared the strength of the glass. If the stresses does not exceed the strength of the glass, it means the glass design is suitable for the application. Let's start by preparing the design thickness geometry. For 2D geometry, 3 separate files are required: the neck, blow mold, and internal profile. The last part of the file name must have an identifier, and they have to be aligned to the neckring line and center line. For this example, the design thickness has a wall thickness of 2 mm and 4 mm for the base. As this is a round bottle, the user only needs to prepare the right-hand half of the drawings, and the other half will be drawn automatically when imported in Elfen GD. Follow the geometry requirements outlined just now and make sure the units are in millimeters. Now export them into IGs or DXF format. They are now ready to be imported into Elfen gd3D. Step 2. Set up Integrity project in Elfen gd3D. In the software, create an integrity configuration and import the geometry created. A revolved 3D bottle will be created with a thickness as specified in the drawing. Now go to Simulation Controls, select Head and Internal Pressure Loading and press Run Simulation. After the simulation has completed, let's assess the result. The default view has 3 graphs. One showing the cross-sectional area of the container, one showing the stress in the inner surface at that section angle, and one for the stress in the outer surface. Now, to have a better understanding what happens to the bottle, let's go the rendered view. Change the loading to head loading only and apply a load of 5,000 newtons. The hot colors mean these areas develop high tensile stress, while the cold colors mean it's under compression. The user have the option to assess the inner surface stress distribution and the stress distribution for outer surface independently. This plot allows the user establish the areas of high risk of breakage, which are the areas of high tensile stresses. Finally, return to the default view. Compare the stress against the strength of the glass, which is defined as a target stress in the software. In this example, we are using a conservative criteria assuming poor handling conditions. The magnitude is defined based on the likelihood of damage of different zones. When comparing, it is shown that the stress induced in the container does not exceed the strength of the glass. Hence, this is a suitable design thickness for our application. Stage 2. Test tooling geometry and machine settings. In this stage, a forming simulation is performed to review tooling design and the machine settings used. The primary output for this simulation is a prediction of the thickness distribution for the bottle. Review the thickness distribution against the design thickness and make the necessary changes to the tooling geometry or machine settings if required. Let's prepare the tooling geometry. For forming projects, 4 separate files are required: the blank mold, the blow mold, neckring, and the plug or plunger depending on the process type. The last part of the file name must have an identifier, and they have to be aligned to the neckring line and center line. As this is a round bottle, the user only needs to prepare the right-hand half of the drawings, and the other half will be drawn automatically when imported in Elfen GD. Follow the geometry requirements outlined just now and make sure the units are in millimeters. Now export them into IGs or DXF format. They are now ready to be imported into Elfen gd3D. Step 2. Set up forming project in Elfen gd3D. Navigate to Furnace in the Forming section and select the material properties for this project. A predefined glass mix is chosen in this example. However, a viscosity calculator based on oxides is provided if required. Now create a narrow neck press blow line by selecting Add Line, and navigate to Geometry and import the geometry prepared. Provide the information on tooling position defined by initial plunger position and final plunger tip baffle distance. The information on the gob is characterized based on gob weight, which calculated as the volumes, and increment crown position and edge, which determine the shape of the gob. The crown position moves the tip of the gob, forming the crown, and the crown edge moves the edges, which allows further refinement of the gob shape. Now navigate to process details and define the pressure or force data in the forming process. Now define the temperature of the gob and the tools. The tool temperature can be either defined as a uniform temperature or a specified temperature distribution. The default temperature for mold temperature is used. Finally, navigate to machine timings and define the machine speed and event timings. These inputs can be obtained directly from an IS machine. To run the simulation, navigate to Simulation Controls and press Run Simulation. The software will generate a data file and start the simulation. The only thing to do now is to wait for it to complete. Once the forming simulation is completed, let's assess the result. The default view consists of two main plots, a cross-sectional plot and a thickness distribution graph. The user has the option to scroll through the forming events or look at different section angles. When comparing the thickness results against the design thickness, it shows that the thickness distribution resembles the design thickness, which indicates the tooling geometry and machine timings is suitable for the application. But let's say we want to improve the thickness distribution in this location. Stage 3. Review and iterate design. In this stage, sensitivity tests on the tooling geometry or the machine timing are performed in effort to improve the glass distribution. To set up a sensitivity test, simply copy the configuration that was run previously and make the modifications to the new configuration. In this example, the final blow-on was brought forward to reduce rundown. Then go to Simulation Control and run the simulation. Once the simulation is completed, let's compare it against the base case by clicking on this button in the corner and selecting both simulations. Now assess the effects of the changes made, with the blue line representing the base case and the red line the sensitivity. The results show that the change in timing made the neck area thicker, which is what we wanted. As a final check, perform a stress analysis on forming thickness by creating another integrity configuration. In the Use Forming Geometry section, select the sensitivity simulation. This will import the forming thickness result as the geometry for an integrity test. Now, go to Simulation Control, select Head Load and Internal Pressure Loading and press Run Simulation. Let's assess the result. First, make sure the loading conditions is as the what was used in stage 1. And compare it against the target stresses used when determining the design thickness. When comparing, it is shown that the stress induced in the container does not exceed the strength of the glass. Hence, the tooling geometry and machine timings can now be passed down to the production line in a PDF format to start machine trials.